Good morning. Today we are going to discuss about different types of transistor connections. That is, how a transistor is being connected when it is introduced in a circuit. So you know that a transistor has three regions: emitter, base and collector. So and the emitter base region is forward biased and the collector base junction is reverse biased. So we need at least 4 terminals for it is to be introduced in a circuit. So this is quite difficult when it is introduced in a circuit. So in order to overcome this difficulty, we can keep one of these terminal as common to the other two. That is, we have three regions: emitter, base and collector. So the transistor can be introduced in the circuit as in three ways, with any of this region common to the other. According to that, we can have three types of configurations. That is common base connection, common emitter connection and common collector connection. In common base connection, the base region is common to both emitter and collector. Okay, and in the common emitter connection, the emitter is keeping common to base and collector. And similarly, in the common collector connection, the collector region is keeping common to both emitter and base. Okay, so this is the configurations, different configurations that we are used while we are introducing a transistor in a circuit. Each circuit connection has specific advantages and disadvantages. It may be noted that regardless of circuit connection, the emitter is always forward biased in the forward direction, while the collector always has reverse bias. So whatever be the configuration we are using, the emitter is always forward biased and the collector is always reverse biased. So that's the condition. Okay, so we can have all these all the three configuration, but this condition should be kept. Okay, so these are the three configuration. So we will know about what are this configuration. So first one is common base connection. So in common base connection, you can see in this picture, this is emitter, this is collector and this is base. Okay, so this is an NPN transistor and here it is a PNP transistor. You can recognize it by noticing the direction of arrow. So in this arrangement, here this is the base terminal and this is the emitter and this is the collector. Here you can see that this base is connected common to both emitter and collector. So this is how this configuration this is how in this configuration the transistor is introduced in the circuit. That is, the base region is being kept common to both emitter and collector. So this is the common base configuration. Okay, so you can note here that the emitter base junction is forward biased by connecting the negative terminal to the emitter and positive terminal to the base. Since it is NPN transistor, it is being forward biased by this connection, and by this connection this is being reverse biased. And similarly for PNP transistor, the emitter here also the base is common to both emitter and collector, and here also the emitter base junction is forward biased and base collector junction is reverse biased. Okay, so this is about common base configuration. So the next one is common emitter configuration. So in the common emitter range configuration, the input is supplied between base and emitter, and the output is taken from collector and emitter. Here the emitter of the transistor is common to both input and output circuits, and hence the name common emitter connection. Just we have seen in the previous picture. This is common emitter. Here you can see the emitter is being made common to both base and collector region. Here it is NPN and this is PNP transistor. Okay, so this is the common emitter configuration. Here base current amplification factor is known as is represented by beta. In common emitter connection, the input current is IB. You can see this is the input region, so this IB is the input current and the output current is collector. Okay, so the ratio of the change in collector current to the change in base current is known as the current amplification factor. So we can represent beta, the base current amplification factor, as delta IC by delta IA. That is the ratio of output current to input current. Here the output current is IC and input current is IB. So the ratio of the change in output current to change in input current gives you the amplification factor. In case of common emitter configuration, the output current is IC and input current is IB. Okay. In almost any transistor, less than 5% of emitter current flows as base current. Therefore, the value of beta is generally greater than 20. Usually, its value ranges from 20 to 500. This type of connection is frequently used as it gives appreciable current gain as well as voltage gain. Okay, so we can said that in almost every transistor, less than 5% of emitter current flows as the base current. So the base current is very small. Therefore, the value of beta is generally greater than 20, since the IB is in the denominator. So this value is is large, and it can vary from 20 to 500. Okay. This type of connection is hence appreciable because current gain and voltage gain are appreciable in this case. Okay. Now we can see the relation between alpha and beta. So what is alpha? Alpha is the current amplification factor in common base configuration. Common base means base is common to both emitter and collector. Just we have seen in the previous the first configuration. So in that collector current is the output current and emitter current is the input current. So the ratio of change in output current to change in input current gives you the amplification factor in alpha in common base configuration. So alpha is nothing but delta IC by delta IE, where IC is the output current and IE is the input current. So that delta IC is the change in output current and delta IE is the change in input current in the common base configuration. This is the corresponding values in the common emitter configuration. So alpha and beta are nothing but the current amplification factor, where alpha is in the common base configuration and beta is in the common emitter configuration. Okay. Now in the transistor, IE is the sum of the emitter current is the sum of base current and collector current. So we can write IE as IB plus IC. So we can represent the change in emitter current as delta IE as delta IB plus delta IC. Okay. So that delta IB is equal to delta IE minus delta IC. Okay. Now if we substitute the value of delta IB in this expression of beta, we get beta is equal to delta IC by instead of delta IB we can substitute delta IE minus delta IC. Okay, so we get beta as like this. Now divide the numerator and denominator of this RHS by delta IE. So what we will get? Delta IC by delta IE, and in the denominator delta IE by delta IE minus delta IC by delta IE. So delta IC by delta IE is nothing but alpha. So we can replace this term by alpha, and delta IE by delta IE is 1, and this term is again alpha. So alpha by 1 minus alpha. So you can see that beta is equal to alpha by 1 minus alpha. So this is the relation between alpha and beta, where alpha and beta are the current amplification factor in common base and common emitter configuration respectively. It is clear that as alpha approaches unity, beta approaches infinity. If alpha is 1, this denominator becomes 0. That means beta tends to infinity. In other words, the current gain in common emitter connection is very high. It is due to this reason that this circuit arrangement is used in about 90 to 95% of all transistor applications. So because of this reason, majority of the circuit configuration use this configuration. Okay. So this is about common base configuration. Okay, and we have seen the relation between alpha and beta and current amplification factors. So we are not going to discuss the expression for collector error, which is out of your syllabus. And now we'll move on to, so we have discussed common base and common emitter configuration. Now we will discuss about let me see. Yes, characteristics of common emitter connection. There are common emitter characteristics, common base and common collector characteristics, but we will discuss only the common emitter connection because your syllabus have listed only this. So we are not going to discuss the others. So we will discuss the characteristics of common emitter connection. So the important characteristics of the circuit arrangement are the input characteristics and output characteristics. So this is the connection diagram for common emitter characteristics. Okay, so this is the battery, and this is a variable resistor, and that is the value can be changed. We can use rheostat if you are doing it in a lab. And this is micrometer, and this is voltmeter, in order to measure the voltage between base and emitter. That is why it is suffixed as BE, base emitter voltage. And this is millimeter. Here you can see that here it is micrometer and here it is millimeter. This is because this is base, so the base current is very small, so it can be measured with a micrometer. A millimeter may not read the base current value sometimes because that current is that much small. And the collector and here it is millimeter. Okay, and this is voltmeter, which measures the voltage between collector and emitter, that is why CE. And this is again a variable resistor with power supply. Okay, so this is the connection diagram for drawing the characteristics in common emitter configuration. So we can see the input characteristics. So it is a curve between base current IB and base emitter voltage VE at constant collector emitter voltage. So what is the input characteristics? Input characteristics mean the graph between input values, that is graph between input current and input voltage, that is IB and VBE at constant output voltage. Output voltage means collector emitter voltage, that is VCE. So this is the graph IB, this is the input current, and this is VBE, this is the input voltage at constant VCE. So here we have shown two curves at VCE 10 volt and VCE 1 volt. Okay, the input characteristics of CE connection can be determined by the circuit as shown in figure, keeping VCE constant. Note that the base current IB for various values of VBE. Then plot the readings obtained on the graph, taking IB along y-axis and VBE along x-axis. This gives the input characteristics at VCE 10 volt as shown figure. Following a similar procedure, a family of input characteristics can be done. So this can be drawn for different values of VCE. So what we are doing is we are changing the output voltage VCE. First it is being kept at 1 volt and we can keep it 5 volt and then 10 volt, 15 volt, etc. And for each we are measuring the value of the current for different values of voltages, and we are drawing the graph like this. So this is the input characteristics. Okay, this characteristics resembles that of forward biased diode curve. This is expected since the base emitter section of transistor is a diode and it is forward biased. So this is similar to a forward biased diode. This is because the base emitter junction is similar to a diode. That's why a forward biased diode. As compared to the common base arrangement, IB increases less rapidly with VBE. Therefore, input resistance of CE circuit is higher than that of common base circuit. So we haven't seen the common base arrangement, so we cannot go in detail to that point. Okay. And you just understand that compared to the common base configuration, the input resistance of common emitter circuit is higher than that of the common base circuit. Okay. Now the input resistance of this configuration can be measured as VBE by IB because V by I give you R according to Ohm's law. So the voltage is, input voltage is VBE and input current is IB, and the change in this value or the ratio of the change in this value give you the input resistance at constant VCE. This is the input resistance. Now the output characteristics. So it is a curve between collector current IC and collector emitter voltage at constant base current. So output characteristics means curve between output current and output voltage. Output current is collector current IC and output voltage is emitter collector voltage, that is VCA, at constant IBE. So we can draw similar different curves for different IBs. So what we are doing is we are keeping the IB at 5 microampere, 10, 15, 20 microampere values, and we are measuring the collector current for different values. So collector emitter voltage. So we will get a curve like this. Okay, so we'll get different curves. So this is the output characteristics. So what we are doing in the output characteristic curve. Now the collector current IC varies with VCE for VCE between 0 and 1 volt only. After this, collector current becomes almost constant and independent of VCA. This value of VCA up to which collector current IC changes with VCA is called the knee voltage. The transistors are always operated in the region above the knee voltage. So you can see that the collector current changes like this, and this changes only up to this value, and beyond that it has a steady value. It is constant, almost constant. You can see from this graph. So this voltage is known as new voltage, and up to which the collector current varies. Okay. And the transistors are always operated in the region above this knee voltage. Now above knee voltage, IC is almost constant. However, a small increase in IC with increasing VCE is caused by the collector depletion layer getting wider and capturing a few more majority carriers before electron hole combination occur in this area. So what happens above knee voltage, IC is almost constant. As it is clear from this graph. However, a small current in IC with increasing VC is caused by the collector depletion layer getting wider and capturing a few more majority carriers before electron hole combination occurs in this base area. So that's what's happening there. So for any value of VCA above knee voltage, the collector current IC is approximately equal to beta times IV. Beta, where beta is the current amplification factor. Okay. So so this is obtained from the relation for current amplification factor. So IC is nothing but beta times IB. And also the output resistance can be measured by this relation. Output voltage by output current, change in output voltage by change in output current. Here the output voltage is VC and the output current is IC. So the ratio of change in these values give you the output resistance. Okay. So this is common emitter characteristics. Now you can see the common collector connection. Just we have seen the common base, common emitter connection. The common collector connection is like this, in which the collector is common to both base and emitter. Here you can see this is arrowhead region is the emitter, and the middle terminal is the base, and this is the collector. So in this configuration, the collector is made common to both base and emitter. So this is common collector configuration. This is NPN transistor, and similarly the PNP configuration. Okay, so this is the common collector configuration. Okay. So what we have seen today is we have seen different transistor configuration, in which common emitter, common base and common collector configurations, and we have seen the common emitter configuration in detail, in which we have discussed the current amplification factor and the relation between the amplification factors alpha and beta, etc. Okay, so this is about the different types of configurations used for the transistor circuits. Okay, thank you.